Hello. Wait. Hello. Let me just check if everything's working. Should be fine. Let's see. Okay, cool. Now that people are actually joining in, hello, welcome. It's like my first time streaming, bro. And like, it's pretty cool to like actually see myself on YouTube. Anyway, we just wait for a couple minutes. I just want to see. Oh, okay. Whoever's here, like, just so I know people are watching, can you just like type something in chat? All right. Let's see. Okay, I'm getting like a good number of responses. This is so cool, bro. It's like my first time streaming actually. It's like properly. It's very exciting for me. Cool. Okay. We'll just wait for like 2 more minutes. Let everyone join in, then we'll start. Okay. Okay. Cool. I am noticing that the stream's running at a bit of a delay, so I can't really like read the chat like in real time. But yeah, it's nice to see everyone like coming in. Okay. All right. Look, today is going to be a very engaging and very fun session. Okay, it's about how. Okay, so a bit of like background before I start off. At first, the um whatever I'm teaching, it's gonna seem like a bit theoretical. Okay, it's gonna seem like it has nothing to do with like electronics or robotics or anything close to that. But believe me, by the end of the session, you're gonna see why I taught everything I did and um how it all comes together to like actually how we actually use everything to like build something in the real world which actually serves a real purpose. Okay, it's gonna be really fun. Uh, can't wait to like get into it. Cool. Let's see some more responses, then we'll start. No, this is my home, bro. Hostels aren't this nice. I have like a whole bed over here. You'll never get this in a hostel, like a proper bed. All right. Okay. So we'll get started then. Okay. Cool. First, okay. Let's switch over real quick. I hope you can see the presentation now. Okay. Uh, just a second. All right. Okay. So, the session is gonna be about digital systems and a brief introduction to like microcontrollers. Okay, that is what we're gonna be covering in this session. Cool. Okay. Now, a brief like overview of what we're gonna cover today. First of all, we're gonna look at binary logic and logic gates, which I'm pretty sure most of you know. Even if you don't, it's fine. I'm gonna start from absolute scratch. This entire session, if you know nothing about if you know nothing in general, you're gonna get everything by then. So yeah, we're gonna start off with basic binary logic and logic gates, stuff like OR gates, AND gates, and NOT gates. Okay, and up next we're gonna talk about how we're gonna design a logic circuit for any truth table. Now, I'll get into what each term means, what a logic circuit is, what a truth table is, if you guys don't know later. Okay, that's what we're gonna be doing. And then we're gonna be designing a combinational circuits with multiple inputs. Okay, uh, that's supposed to say outputs. My bad. Outputs. That's my bad, guys. Okay. Combinational circuits with multiple outputs. And then we're gonna take an example of a half adder. If you don't know what that is, again, I'm gonna start from absolute scratch. Okay, I'm gonna tell you what a half adder is, how you add binary numbers and all that. Okay. Um. Oh yeah, I have a full wall of monster cans. I forgot to take that up, bro. But I'm pretty proud of it. All right. Okay. Well, I forgot to introduce myself again. Okay, I'm Atit. I'm about to enter my second year in IIT Madras. I'm from engineering physics, which is a branch in IIT Madras. I'm part of it. I'm from Chennai. I live here. Okay, cool. Anyway, moving on. We have Up next, after that, we have I'll introduce you to some basic digital circuit components. Okay. What that essentially means is after you look at all of the theory behind like digital systems and binary logic, we're gonna see how um, different real world like chips and real world components are used to build something in the real world. Okay, I'm gonna give you a bunch of examples. It's gonna make a lot of sense. Cool. Now, after that, we're gonna look at memory elements, which means I'll get into it in detail later. But memory elements essentially it allows the circuit to remember past inputs. Okay, so that's where your memory comes in. Any sort of memory you have on your computer or like any kind of circuitry comes from memory elements. Cool. And at last, I'm gonna introduce you to the idea of microcontrollers, and I'm gonna take the example of the Atmega. Now, primarily, I included the microcontrollers part as a sort of payoff at the end. Like you're gonna see how every single concept throughout the session is gonna culminate into how you understand microcontrollers. Okay. Cool. All right. So that's pretty much it. Let's get into it. Okay. First we're gonna talk about binary logic and logic gates. Okay. I'm sure most of you have at least like come across the idea of how we use zeros and ones as an equivalent for true and false. False and true. It's the other way around. Okay. Zero is false and one is true. If you don't know what that means intuitively right now, I'll tell you later, but it's fine. As of right now, just know that we use a zero to um represent the idea of something being false, and one as to represent an idea of something being true. Okay, cool. Then there's something called logic gates, which again from the WhatsApp poll that I released. I think most of you know what it is. I'm gonna get into it anyway. Okay, let's see. Oh, this is my bad. Sorry. Yeah. Okay. So, what is a logic gate? Now, as I said before, uh, you have zeros and ones, right? Which represent the idea of something being false and true. Okay. Now, when you're designing an electric circuit or a computer, you can't, you only communicate and you only work with data in the form of different things being false and different things being true. Okay. So, just a very surface level example, let's say, is uh, let's say you want to turn an LED on. You define the LED being on as 1 or true. Okay. If you give the input true or 1, the LED turns on. And if you give the input 0 or false, the LED goes off. Okay. That is a very rudimentary example. Okay. For how we use zeros and ones to represent data and how it actually affects things in the real world. Okay. Now, how we manipulate zeros and ones is through something called logic gates. Okay. Now, I'm going to introduce you to 3 different logic gates. Okay. There are more, but as of right now, we're just going to talk about 3 gates. Cool. These are gates. I'll tell you what each of the symbols mean. Okay. First, let's go to the NOT gate, which is this. This is the NOT gate. Okay. It has one input and one output. So whatever input you give to the gate, whether it be 0 or 1, it gives the opposite of it. So if I were to give 0 to this gate, again, I'll tell you what this means intuitively later. Just think about this as a very theoretical concept right now. Okay, I give it a zero, I give it a zero or a false, and it turns it into a true. Okay, if I give it a zero, it turns it into a one, and if I give it a one, it turns it into a zero. Cool. That is essentially what a NOT gate does. All right. Now, we'll talk about the AND gate. Oh, sorry, the OR gate. Okay. Now, the OR gate has two inputs. Okay. It has two inputs, both of which you can either give a zero or a one, and accordingly, it'll give some output. Okay. Now, how an OR gate works is either one of the lines that you give, either one of the inputs that you give to the OR gate, if either of them is one, it outputs a one. And if both of them are zero, it outputs a zero. It's pretty simple to understand. Okay. Uh, so if I were to give two zeros to the two input lines, I'm gonna get a zero. And if I give literally anything else, a zero and a one, I'm gonna get a one. If I give a one and a zero, I get a one. And if I give a one and a one, I get a one. Cool. Is that clear? All right. This is what an OR gate does. Okay. Now, an AND gate. It's also pretty straightforward. It has two input lines and one output line. Okay. Uh, this I hope it's better now. Sorry for that. Hope you guys got all that. Sorry. Okay. Before I start again, I hopefully I fixed the network issue. If anything persists, just let me know. All right. Just give me 5 minutes, guys. Like I'll just like sort this out. It's fine now. Is it all right? I hope it is. Okay. If it's fine now, can I continue? Cool. All right. Okay. Fine. Let's get back into it then. I hope everything else was clear except for my video. I hope that wasn't too much of a problem. I hope you understood what I was trying to say. Just anyway, a little bit of a recap just to um cover what you might have missed. Three logic gates. The NOT gate, which if you pass a zero, it gives a one, and if you pass a one, it gives a zero. Essentially, it gives the opposite of what you give. Cool. An OR gate, it has two inputs and one output. As long as you give anything but two zeros, it gives a one. If you give a zero and a zero, it gives a zero. And if you give it literally anything else, it gives a one. Okay, that's called the OR gate. An AND gate, essentially, both the lines have to be one for it to give a one, and if it doesn't, it gives a zero. Okay, I hope this is clear to everyone. All right. Okay, if this is clear, I'll just give one more concept. Okay, how you represent this mathematically is an AND gate is represented. Okay, let's say your input lines, your whatever you're inputting to the gate, let's say it's X and Y, right? X and Y can either be zero or one. Cool. How you represent an AND gate is like multiplication. It's just X, Y. So if X is zero and Y is zero, if X is equal to zero and Y is equal to zero, XY is going to be 0. Cool? I hope that's clear. Uh, okay. Similarly, an OR gate is represented by x plus y if your inputs are x and y. So, in this case, if x is equal to 0 and y is equal to 0, x plus y is also going to be 0. I hope this is clear. It's just a way of like mathematically representing binary inputs and logic gates. Okay. Now, how you represent a NOT gate is through a complement or a line above whatever it is. So, if your input is x, the output is going to be x complement. Okay. So, if x is equal to 0, x complement is going to be 1. I hope this is clear. This if you have to understand this to like understand whatever I'm going to talk about later. Okay, cool. Let's see, what do you guys think? Cool. Okay, I hope this is clear, guys. All right. Next up. Okay, now that you know logic gates and binary as something theoretical, okay, I'll tell you what it means in actuality. Okay. Uh, so give me a second. Okay, so whatever we consider 0 or false is just a 0 volt. Okay, it's 0 voltage. Okay, think about it like that. And whatever we say is 1 or true is 5 volt. Okay, so what it means is that in the real world, a logic gate is nothing but an electronic component which lets voltages flow through it. Okay, so let's take an example of a NOT gate. Okay, if you pass in the real world, if you pass a 0 volt through it, it's gonna give you 5 volts on the other end. And if you give it a 5 volt, it's gonna give you 0 volts on the other end. Okay, is that clear? This is how you represent data in binary form in anything electronic. Okay, is that clear? Similarly, just another example for an OR gate. If 0 is false and 1 is true, we just pass. Let's say we pass a 0 volt and a 5 volt here. Essentially, you're passing a 0 and a 1. And if you pass a 0 and a 1 through through an OR gate, what are you gonna get? You're gonna get a 1, which means the OR gate is nothing but an electronic component which lets the 5 volt through. Is that clear? That is how you think about logic gates in the real world. Well, that's clear, guys. Let's see. Cool. Okay. Now that we have that out of the way, let's move on to the next topic. Okay. Now that you know what a logic circuit is, sorry, now that you know what a logic gate is, I'll tell you what a logic circuit is. Okay. Just give me a second. Uh, hmm. Okay, cool. Now I'm gonna introduce you to a bunch of new terms. Okay. There's something called a truth table. Okay. There's something called a logic circuit. There's something called a combinational circuit. Now, first off, what is a truth table? That's pretty simple to understand. This, whatever I drew here, this thing, this is a truth table. Okay. So, essentially, if I were to draw a truth table for a OR gate, I have my two inputs x and y. Okay, and I have the output which I can call anything. I'm just gonna call it f. Okay, Now, if x is 0 and y is 0, what is f going to be? It's just going to be 0. If x is 0 and y is 1, f is going to be 1. And if x is 1 and y is 0, f is going to be 1 again. And if x is 1 and y is 1, f is going to be 1 again. So, a truth table essentially describes the behavior of a circuit. In this case, the circuit is only made up of one logic gate. But you can have a circuit. I'll give you an example circuit. Okay. Let's say I have two inputs, x and y. Cool. Let's say I have some combination of circuits. Okay. Something like this. Okay. Let's add a NOT gate here as well. Okay. So this is like a circuit which is made up of more than one gate. Uh, if you want to write this down mathematically using the notation I said before, this is just going to be this is an OR gate, right? OR gate is just x plus y, but one of the inputs here is complemented. It has a NOT gate over here, so we're just gonna do that. Okay. Now, uh, the second OR gate over here has x complemented and y not complemented, right? So these are your two inputs to the final AND gate. So essentially, you're just going to represent this circuit using this mathematical expression. You multiply that. Is that clear? Let's see. But how do these logic gates work? Like, what makes them perform their respective functions? Okay, so the thing about that is that in the real world, these gates are built up of transistors. Okay, so inside there's like a bunch of transistors which are arranged in such a way that it provides like the desired output for each gate. That is all you need to know for right now. You're usually gonna have like a preset like set of gates as an IC or an integrated circuit. We'll get to that later. But as of right now, just think of these as like your atoms of a circuit. You don't have to go into what it actually contains because it's kind of like it's way out of like this session at least, like way out of scope. But yeah, you can look into that later. It's just different transistors arranged in a neat way. Okay. X plus. Oh, my bad. Okay, sorry. I that's my bad. Sorry. All right. So just scratch that. It's just X. I made a mistake. Yeah. Yeah. Okay, cool. So, I hope you guys get how we got this out of the circuit. Okay. What else? Okay. Now, for you to understand what the behavior of one like full circuit is, you can represent that entire circuit, you can represent its whole behavior as a truth table. Okay, so let's try to figure out what the truth table is of this equivalent circuit. Okay, let's try drawing x, y, and we'll call the output f. Okay, uh, cool. Sorry, something like that, right? We'll just like look at different cases, which are just 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now, when x is 0 and y is 0, what do you get? You get 0 plus 0, 0 complement, times 0 complement plus 0, which is 0 plus which is just 0 plus 1 times 1 plus 0, which is just 1 plus 0 is just 1, and 0 plus 1 is just 1. If you These are just like gates, right? We're just representing them in like a mathematical way, and this essentially just comes out to a 1. Cool. All right. Now, next case, 0 and 1. We just get through this quicker, okay? Uh, the next case is just 0 plus 0 times 1 plus 1, which just comes out to 0. Okay. Now, let's see. So the third case, it's just 1 plus 0 times, 1 plus 0 complement, which is 1 times 0 plus 0, which comes out to a 0. Cool. And the last case, it's just 1 plus 0 times 1 plus 0, which comes out to a 1. Okay. You can work this out yourself. This is like pretty trivial, I feel like. Okay, so finally, for this circuit, which is made of multiple logic gates, you get one finalized truth table. Okay, so a truth table is essentially a way for you to summarize the behavior of a circuit. Hope that's clear. Okay. Now, again, when I say a binary function is just a circuit. Okay, a binary function basically means you take some input x and y and you give an output f. Without going into too much detail, this is what a function is. This is what a binary function is. And each binary function theoretically can be represented by a circuit, a binary circuit. Okay, so off the top of my head, okay, I'm just gonna say I want a circuit which gives me, let's say I want a circuit which takes in two inputs and it needs to give me a, it needs to give me a 1 only if both of them are different. Both x and y inputs are different. So the equivalent truth table for that is going to be, okay, so the equivalent truth table is going to be 0, 1, 1, and 0, because only in these two cases are the inputs are different, 0, 1, and 1, 0. Okay, this is a theoretical binary function, and I can realize it using a bunch of logic gates. How exactly can I do it for any theoretical function? We'll get into that. Okay. Okay. Now, this is where you get into something called SOP, or canonical forms. Okay. This is like essentially a way for you to realize any binary function as a combinational circuit. A combinational circuit is nothing but a circuit with a bunch of logic gates. Okay. How you realize this function as a circuit is basically you're gonna okay, so I want you to think of this intuitively. Okay, you want to cover every single case. You want to cover every single case of the truth table. Let's look at xy. Okay, where x is equal to 0 and y is equal to 0. Now, when x is equal to 0 and y is equal to 0, you want your function to output a 0. Okay, so when x is equal to 0 and y is equal to 0, you want a 0. Okay, now let's look at this case. When x is equal to 0 and y is equal to 1, you want your function to output a 1. How do you represent this as in a mathematical way? Okay, now you want your final mathematical function, mathematical binary function, to have a term sorry, x complement y. Because think about it. If you have something, if you have your function f as x complement y plus something else, whatever it may be, for this case alone, you're gonna end up having the function, you're gonna end up having f as 1. Because when you input a 0 and you input a 1 over here, 0 and a 1, this term becomes 1. So whatever this is, we don't really care, because as long as this is there in our function, this term is there in our function, for this case alone, for this case alone, f is going to turn out to be 1. Is that clear? Cool. Now, similarly, when x is equal to 1 and y is equal to 0, again you want your f to be 1. Okay, so what do? You add another term. You add another term, x y complement. Is that clear? X y complement. Why? Because if you put x is equal to 1 and y is equal to 0, for this case alone, if you input those values, whatever the other part of the function, we don't really care, because this term ends up becoming 1 for that singular case. So f winds up being 1. Okay. So what I'm trying to say is, for any truth table, okay, I'm just gonna clear this out. I'm just gonna clear this out. For any truth table, there's something called a canonical form, which essentially means, wait, let me just delete that. Okay, which essentially means you take whatever case that f winds up being 1 in. In this case, it's 0, 1, and 1, 0. Okay. So for the first case, my term is going to be x complement y, because my y is 1 and my x is 0. For each case, you take whatever variable is 0 in that case, you and then you complement it. Okay, so in this case, your term ends up being x complement y. And in this second case where f winds up becoming 1, you have x y complement. Similarly, because x is 1 here, we're leaving it as is. Y is 0 here, we're complementing it. Okay, now you have these little terms, right? You have x complement y and x y complement. Your final function is nothing but x, these terms added together. Okay, I hope that's clear. This is it's pretty important to understand whatever I'm going to be talking about. Okay, I'm just going to wait for responses, because this is like a pretty like theoretically heavy topic. I hope everyone understands it. I'm just going to wait for some responses. Yeah, is this clear? Cool. Okay. All right. Okay. Cool. Now that you guys get it, this way of realizing a binary function as a mathematical expression is called SOP, which is the sum of product. Why is it called that? You can see it. See, it's just a bunch of products which are added together. Okay. Okay. This is called the sum of product, or SOP canonical form. The name doesn't really matter. So all that matters is you know how to realize any binary function. So if I give you a problem statement, uh, I want you to like try this at home, like kind of like a homework if you want. Um, let's say I have three variables, right? X, Y, and Z, and I want a function f which takes in X, Y, Z, and it only gives a one. It only gives a one if two or more variables are 1. That's clear. I want you guys to try this out at home. It should be pretty straightforward if you understood this clearly. Uh, yeah, this is just like an expansion of the idea into three variables. You can have this for any number of variables actually. This is just like a case off the top of my head. Cool. I want you guys to try this out at home. Anyway, this is how you realize a binary function as a mathematical expression. Cool. Now, we'll get to what don't cares is. Okay. Now, how don't cares work is essentially it's pretty straightforward. Okay, I'm gonna take this example again, where if they differ in value, you output a one, and if they're the same, you output a zero. Cool. Essentially, don't cares are just okay. So let me alter my problem statement. Okay, let me say if uh if they're the same, if x and y are the same, I don't really care what happens with the output because uh, that's not really. Let's say I have a situation where that's not really gonna happen in the real world by the user. Okay, so I just instead of me wanting a strict zero, it can be anything. That is what I don't care is. Okay, all right. So instead of a one, instead of a zero, I'm gonna represent it by an x. Now, this doesn't really change your final output. Okay, I just wanted to introduce this concept because, okay, let me get one thing clear. Okay, this final output that you get from this whole procedure of SOP, this is not the most simple circuit that you can get for the given problem statement. Like not even close. You're gonna get a very complex circuit, but it's gonna do its job. You're just gonna have to use way more logic gates than what's actually required. Okay, which in the real world is pretty wasteful. Okay. Now, why don't cares come in handy is when you're trying to simplify it, when you're trying to simplify the circuit, and I'll tell you how to later. When you're trying to simplify the circuit, sometimes it helps to not care about certain cases. It simplifies the circuit more in that case. Okay, so that is why don't cares are very essential. If you assume that some cases in your truth table aren't really going to happen in the real world, then you can use a don't care and you can make your circuit so much more simpler. Okay, now if this is not the most simple version of the circuit, how do you realize the most simple version? And for that there's something called a k-map. Okay, I'm not going to get into it because it's like very theoretical. I'll give you some resources later. Okay. Uh, I've included in the PPT here. Oh, sorry. Designing the simplest circuit possible for a given truth table, you use something called a K-map. Okay. It's very procedural. You draw like, I'm just going to give you a very, very brief overview. You're going to draw a bunch of like squares. You're going to put zeros and ones here and you're going to group stuff together. Okay, it works like that. It's very like simple, but it allows you to realize the most logic gate efficient way to realize a circuit. And don't cares help it simplify it even more. Okay, is that clear? Let's see. I guess if some cases aren't practically possible, then we'll exclude it. Yeah, exactly. So in that case, don't cares come in very handy. I'm gonna wait for some people to say it's clear or not clear, and I'm gonna move on. Let's see. I hope you guys are finding this like interesting, by the way. When I was learning it like for the first time, I found it like really interesting that we can do this out of like just like voltages and stuff. Okay, fine, it's clear. Cool. Okay. Fine, then we'll move on. Next up, we have okay, combinational circuits with multiple outputs. Pretty straightforward, right? Over here I have an output F, and this is the only output that I'm working with, right? Now let's say I need a circuit which takes in two inputs and I need two outputs. Okay, something like this. Yeah, and I want the truth table for which is going to look like this. Let's say for my output F, I want it to just straight up be an AND gate. Okay, so I want this to be a 0 and these cases to be 0 and only this case to be a 1. And for my second output G, I want the old problem statement, which is if it differs, I need a 1. If it's the same input, I need a 0. Okay. In that case, it's just going to be 0, 1, 1, and 0. Okay. How are you going to design a circuit with two outputs exactly? Nothing out of the blue. It's just you're going to design two separate circuits and you're going to merge them together. Okay. So I'm going to take the case of F first. Okay. It's 0, 0, 0, and 1, which means for the only case where it's 1 is the final case, which is when X and Y are 1. So using the SOP method, I'm just going to get XY. So my final expression is just going to be XY, which is just an AND gate, as I said. Now, for my G, I'm going to write it here. My terms which are going to give a 1 are just going to be X complement Y and XY complement. So my G is just going to be, XY complement. So my G is just going to be X complement Y plus XY complement. Okay. Now, how I'm gonna realize the circuit exactly is just pretty straightforward. Let's say these are my inputs X and Y. Of course, my F is just gonna be a single AND gate. Okay, that's my F done. And for my G, it's gonna be a bit more complex, but I'm gonna have an OR gate at the end, which is gonna give me my G, and two AND gates. Okay. X complement Y. I'm sorry, my diagram's too messy. I hope you get the idea anyway. And X Y complement. This is my final circuit. Now notice how this is different from the other circuits that we discussed in the sense that we have two inputs and two outputs. That is what the biggest takeaway is here. For to design a combinational circuit with which gives more than one output, you're just gonna do each of the functions separately and you're gonna combine it into one big circuit. Okay, I hope that's clear. Let's see. Play a drum set? What do you mean, bro? Did I? No, I didn't. Okay, I don't know what that means. But anyway, cool. Now, just so the concept is absolutely clear, I'm gonna derive something called a half adder. Okay. Now, what a half adder is? For you to understand that, first of all, I need you to understand what binary addition is, or like the very basic understanding of what binary addition is. Okay. So, like when you add two numbers like 10 and 12, you just get you're adding like 0 and 2 together, and there's no carry here, so it's just 1 plus 1, which is 2. This is pretty simple, right? So in the case of binary addition, okay, you have these cases. Okay, so 1 plus 1 is just going to be if you're gonna add 1 and 1, you're gonna get a 0 here and a carry 1. Okay, I hope this is clear. Like if you add a 0 and 0, you're gonna get a 0. If you're gonna add a 0 and a 1, you're gonna get a 1. if you're gonna add a 1 and a 0, you're gonna get a 1 again. And if you're gonna add two ones together, it's gonna give you 1 and a carry. So like when you're doing this but in binary, uh let's say I'm gonna add two binary numbers, like 1 1 plus 1 0. Okay. If I'm gonna do this, so in my first column, there's 0 and 1. And as I said over here, 0 and 1 gives me a 1 with no carry. Okay. So it's going to give me a 1, and there's not going to be a carry over here. And when I add 1 and a 1, it's going to give me a 0 here and a carry, but there's no column here, so I'm going to write 1 over here. I hope this is clear. Like, this is, I'm assuming, pretty straightforward, no? Let me see. Yeah. Cool. Okay, so this is binary addition, like a very simple understanding of binary addition. Now, what a half adder does, okay, what a half adder aims to do is do this process for me. Okay, so let's say I have X and a Y, which are these two inputs. Okay, I'm gonna have two outputs from the half adder circuit. I'm gonna call it sum and carry. Okay, now what's my truth table gonna be? What's my truth table gonna look like? It's just 0 0 0 1 1 0 and 1 1. Okay, so these are my cases. Now, as I said before, when there's a 0 and a 0, your sum becomes 0. Okay, when there's a 0 and a 1, or a 1 and a 0, your sum becomes 1. And when there's a 1 and a 1, your sum becomes 0 and your carry becomes 1. Okay, so my equivalent truth table is going to look like this. Okay, is that clear? So this is my truth table for a half adder. I'm gonna give it two inputs. It's gonna add it in binary, and it's gonna give me a sum and a carry. Okay. So this circuit essentially takes care of one row operation, sorry, one column operation when we're like adding two binary numbers, like this. So 0 and a 1, it's gonna give me two outputs. Okay. Cool. Now, how you're gonna realize this again? I think I did this exact same thing before, bro. Yeah, I did. Okay, so it's funny because when I derived this, it's by okay. So this example is off the top of my head. I didn't realize this is the same as a half adder, but the truth table, as you can see, is the exact same. From my last example, my F is just C, which is my carry, and my G is just S. So this is my final circuit for a half adder. It's not the most simple version, but it works. This is the most simple version. What this and this gate, I haven't gotten to it yet, but this gate is just called a. I'm blanking. It's a NOR gate. What? No, I'm blanking, bro. Oh my god. A XOR gate. Yeah, my bad. Okay, so this is called a XOR gate, and it's represented by X plus this circle plus Y. Okay, it's called exclusively OR. What that means is that if it differs, it gives a 1. And if it doesn't differ, it gives a 0. Okay, it's called a XOR gate. And that's what we're using in the most simple version of a half adder. But if you're gonna derive it using the SOP canonical form, it's gonna give you this bigger circuit. You realize why this is not feasible in like the real world. It's gonna take up so much more space than this simple circuit. Okay. Hope this is clear, guys. Let's see. Yeah, but why does this kind of addition give the same result as the normal addition in base 10? I mean, it doesn't though. I don't know what you mean. Like, when you're adding two binary numbers, it's the same mechanism, but then it's not really the same. Like, when you're adding 1 and a 1 in binary, you're gonna get a 0 here and a carry here. I hope that's clear. Okay, cool. I'm gonna move on. Okay. Hope that's clear. All right. Now, with that out of the way, let's see what's next. Okay, cool. Now, I'll tell you what an IC is. It's called an integrated circuit. Okay, it looks like this. It looks like this spider-looking thing. Okay. Uh, Essentially, whatever circuitry we've been designing, there is a way for you to like compress it into this tiny ass chip. Okay, so this thing, it's like this big. Okay, and these have like uh digital circuits inside. So these pins, they act as your input. Okay, these little pins. So if you give voltages here like 5 volt and stuff, it's gonna act accordingly, according to like how it's designed inside, and it's gonna give you an appropriate output. In it's some of these are designated as output, some of these are designated as input based on what IC it is. But yeah, essentially an IC is just a very tiny circuit. It's a chip. Okay. Now, we're gonna get into some basic digital circuit components. Okay. Now, what these mean are just different ICs in the real world. They are different ICs which have been designed. Like as you can see, this is called an encoder. I'll tell you what an encoder is, but this is a real world IC. It looks like this. Okay. In the real world, it looks like this. It's called the model is called a 74LS148. You don't really need to know what it is. It's just an IC. It's called an encoder, and this is designed such that it's designed using the principles that we talked about, uh, like the OR gates. They're taking the inputs. Okay, so this component has 8 inputs, and it has three outputs. This one's just optional. We'll get to that later, but uh, these three are the outputs, and it takes in 8 inputs. Okay, and it uses circuitry and like the principles that we discussed before to give those three outputs. Okay, so I'll tell you what the problem statement of the encoder is. Essentially, what it does with the 8 inputs. Okay, so an encoder, let's say you have some use case. Okay, you have 8 lines, and you have a situation such that only one of these lines can be high, or one at a time. Let's say that is your use case. Like there is no possible way that two or more of these can be one at a time. Now there is a way for you to compress the same data or the same information into 3 lines instead of 8. It's gonna save you much more space and much more like circuitry basically, because you already know that only one of these is going to be high at a time. Okay, only one of these is going to be one at a time. So you can minimize the number of lines you use, because if you know one of these lines is 1, the others are redundant because you know that they're going to be 0. So instead of using 8, you can compress all that information. You can compress the information of which of the 8 is 1 into 3 lines. That's all you need. Okay, that is exactly what an encoder does. So what an encoder does is it takes the 8 lines, out of which only one can be true, or one can be at 5 volt at a time. Okay, and it outputs 3 lines. So if my pin, I'm gonna call these 0 to 7. Okay, 0, 1, 2, 3, 4, 5, 6, and 7. So these are my lines, 0 to 7. If my 0 line is at 1, it should output 0 0 0. Okay. If my 1 line is at 1, it should output 0 0 1. If my 2 line is high, it should okay, so high means 1 basically. That's I use it interchangeably. You can also use it interchangeably. It's fine. So 2 is when 2 is high, or when 2 is 1, it should output 0 1 0, and if 3 is high, it should output 0 0, sorry, 0 1 1, 0 1 1, and so on. I hope you get the idea. What this does is it compresses the amount of lines needed to convey the same information. Okay. This is called an encoder. I'm pretty sure you can use the same like SOP method that I talked about to realize this into like a real world circuit, or like a theoretical. I am pretty sure you can draw a circuit like which does the same job as that the encoder does. Okay, you can try it also at home. It's I advise you to do so. But this is the final circuit. Okay, it takes these lines. It has 3 OR gates and gives 3 outputs. And coming to the real world IC, again, this looks like the chip over here. Okay, each of these pins correspond to each of these lines. So how this works in the real world is your 8 lines are 0 1 2 3 4 5 6 7. Okay, and the output of this is going to be A0, A1, and A2. You can like kind of ignore the other pins right now. They aren't really like really necessary. Okay, for the general working, they have like additional use cases, but that's not really necessary for like understanding right now. Okay, so you have 8 lines, 8 input lines, 3 output lines, and I'll tell you what VCC and ground is. Okay, now an IC is in magic. Okay, so when you're giving a 5 volt, it doesn't really know what a 5 volt is. Okay, all it does is it takes in some voltage and it redistributes it among the given pins. It can't really generate voltage out of nowhere. Okay, so what you do is that you set the ground at 0 volt. Okay, and you set the VCC at 5 volt. You do this because you need the IC, you need some kind of reference for the IC. So whatever voltage difference it has between VCC and ground, the circuit merely just like redistributes it among the pins. So whatever voltage difference it has, in this case it's 5 volt, it takes that voltage difference and applies it to certain pins based on what you input. Is that clear? I hope that's clear, guys. Let's see. A lot of messages here. Let's see. If we convert same answer as if. Okay, so Divit is asking if we convert 11 plus 12 in binary, then add it. And convert the binary answer to base 10, then we get the same answer as if adding in base 10. Yeah, you do. It's like, okay, so the way I think of it is like a frame of reference, basically. Like, you're not changing the data itself. You're not changing the numbers 11 and 12. You're just adding them in a different way and converting them back. So yeah, it does give you the same answer. Will we learn the circuital/transistor representation of logic gates? Not in this session, no. And to be honest, I don't know it fully myself. I'm just a second year. All I know is like the theoretical aspects of it and like how to work with ICs. But you can check it out. Like, I'll try to give you some resources later if you're really interested. The method of binary addition has been designed in order to make the answer consistent with what you get in base 10. Well, not exactly. It's like saying you convert base 10 into Roman numerals and then add it and then convert it back. It's the same thing, right? It's not really designed for you to like get the same output. Whatever you change it, if you agree upon a system, it's going to give you the same result. It's just a change in like frame of reference. What are those three gates though? Those are OR gates. Those are OR gates. Cool. So it converts the line number from base 10 to binary pretty much. Yeah, that's a pretty way to look at it actually. Yeah. Okay. You can think of it like that, yeah. What does the IC do with the inputs? Yeah, okay. So the IC has like the circuit inside and it manipulates like your signals and like your voltages to give the appropriate output. Hope that's clear, guys. Okay. All right, cool. Fine. Let's see. Okay, so I assume you know what a decoder is by now. Okay, it's just the same thing. You take the three inputs that you get from an encoder, and a decoder essentially converts it back to the original eight inputs. And the real world IC, it's called 74LS138. Okay, these are your this is your like pin out, or like this is like what each pin does. Uh, let's see, what is this? Okay, so O0 to O7, O0 to O7 is just your outputs. Okay, there's like a notation mismatch. I'm sorry about that. I just like took images of a Google, so like they're not really the same. But essentially, these are your outputs, and A0, A1, A2 are your inputs for the decoder. These you can take library. You can like these are for other use cases. You don't really have to know. One thing though, I hope you see the little bar on top of like the O6 and O5 over here. That means that they are active low. Okay, what that means is that they're essentially like a logic shift. So whatever should be one of the output, it outputs a zero. Okay. Some ICs are like that. Some ICs are like funny like that. Okay. If you want it to be like your traditional way of representing ones, you can add a NOT gate here. It's not that big of a deal. Okay. But just know that in like a pinout diagram of an IC, if you see a bar on top of the output, it means it's active low, which means if it's high, it's zero. Okay. So that's clear, guys. Also, VCC ground I explained already. I hope you guys understand. Cool. Okay. All right. We're like at the halfway point. This is the attendance Google form link. I just um scan it and like fill it out. Yeah. Attendance isn't done yet. This is the link. Good timing, guys. I just got to that slide. Okay. Cool. I'm gonna wait here for 5 minutes. Like this is like I'll give you guys a break as well. I need a break also. So yeah. So it is one's complement. Sure, but one's complement is it describes like uh a bunch of binary. It's like taking you can talk about a one's complement of like 0110, like more than one bit. But like I guess it is the one's complement. You're just flipping the bits, yeah. One's complement is something different, and like you can look into that, but it doesn't really apply here. Technically, it's correct though. Is that your hostel room or class? It's my house, bro. It's my room. No hostel room or club room is this nice. So what's up, guys? I'll give you 5 minutes for the attendance. Like meanwhile, you can just like chumma talk. How was the session so far? Do you guys like understand everything? Do you find this interesting as much as I do? Because I find this like really interesting. What branch are you from? I'm from engineering physics. Bro, how did you learn these before second year, bro? Can you play the piano by okay. Any resources? Okay, I'll any for the resources I'll like text in the group. I'll find some resources. And I'll send like uh different links. And thank you guys. Session is amazing. Thank you, thank you. Um you're a good teacher, so what you teach is interesting. Oh, thank you so much, bro. That means so much to me. How do you do electronics with engineering physics branch? So in IIT Madras, engineering physics is like half electrical and half. Sorry, that must have been loud, bro. I'm sorry. Okay. So engineering physics is half physics and half electrical. So whatever I'm teaching right now, I actually learned as part of my coursework in second sem. Um, IITM has physics 2 alongside BE. BE as in biological engineering. Is that what you mean? Uh, can you play the piano, bhaiya? I used to, bro. Like, I got like forced into piano for like 8 years. I can technically play, but I don't really like it. The keyboard behind me is my brother actually plays it. How to get into engineering physics? Like standard J advanced. Like there's nothing else. Why is why is it that only IITM is conducting summer school sessions? I'm not really sure. Uh, it's not the first time. It's like kind of like tradition at this point. Play us something, please. I can't. Like I haven't played in a long time. Engineering physics is a BTech degree. Yeah, it is. How is the first week at IIT? Is it easy to get into hostels and all? Okay, well, I live in Chennai, so technically, like moving in is just like me driving campus. So like, it's not that big of a deal. It wasn't that big of a deal for me. But first week at IIT, it can be fun. It wasn't fun for me. I'm gonna be honest. It can be fun. Like a lot of my friends, they had like so much fun because it's just like a new environment, new people and all. But I was just like homesick, bro. I missed my home, even though it was only 3 kilometers away from my campus. You explain in a very easy to understand manner. Thank you so much. That means so much to me. Uh, it means so much to me because I want to become a teacher in the future. So nice to know that like y'all like how I teach. Made me understand 5 hour lecture in less than two. It's not a 5 hour lecture. I'm telling you, this whatever I taught is like half of my semester. It's this went on for like a very long time, like 1.5 months at least. Okay, cool. All right, we'll get back to it then. Hope you guys filled out the form. Have you sorted the field you want to become a teacher in? No, I'm kind of thinking of like becoming a JE teacher, JE physics teacher. That's like really fun for me because I love JE physics. I also like electronics, so maybe like an electrical professor somewhere in like a university would be pretty cool. So yeah, no, I haven't sorted out whatever I'm gonna teach. Can other college students join iBot? Nah, bro. I mean, no, I don't think so, because there's a whole apping process, and you have to be in campus, like, do that. So yeah. Teaching from engineering physics branch, is there any relation? Not really. I didn't realize there was a correlation like that. Become a good prof in university. Thank you. I'll try. I'll try. Okay, cool guys. Let's get back to the session. All right. Now, this is another basic digital circuit. It's called a comparator. Uh, so I'll just tell you what this does basically. So the circuit might look a bit like daunting at first. There's a lot of stuff going on over here. But essentially okay, so this is a 4-bit comparator that I'm talking about. And what that means is you give okay, so let's say I have two 4-bit numbers. So two 4-bit numbers A and B. Okay. So I let's say A and B are two numbers in binary. So let's say my first number is 1010 and my second number is 0111. Okay. I hope you guys know how to convert binary into decimal. I hope you do. But if you don't, it's just for the first digit you take 1 times 2 to the power 0. For the second digit you take 1 times 2 to the power 1. For the third digit you take 1 times 2 to the power 2. And for the fourth digit, you take 0 times 2 to the power 3 and you add that all up. That is your number in base 10. What that gives you is 1, 2, 4. That's it. And 0. So you add all that up. 1, 2, 3, 7. So 0, 1, 1, 1 is just 7 in binary. Similarly, 1, 0, 1, 0 is 10 in binary. Okay. I hope you guys know that. Even if you don't, I hope you understood what I said. Anyway, let's say our right? Our number A can be represented by 4 bits. Okay. We'll call those bits A3, A2, A1, and A0. Bits are just like one data point, or like 1, 0, or 1. Okay. So in this case, my A3 becomes 1. My A2 becomes 0, my A1 becomes 1, and my A0 becomes 0. Okay. And similarly for B, my B3 becomes what does it become? 0. My B2 becomes 1. My B1 becomes 1. And my B0 becomes 1. Now, what a comparator does is it takes 8 inputs total. 4 bits of A, 4 bits of B, and it has 3 outputs to give. Okay. Those outputs are these: A greater than B, A is equal to B, and A lesser than B. Let's kind of forget about this for now. This is again for like other use cases, which you don't really have to get into right now, just for like understanding. As always, you have your ground and your VCC. Okay. Uh, okay. So in the case that A and B are the same, or like A and B are equal, this goes high. This output goes high, and the rest goes 0. The rest goes low. Okay. Similarly, if A is greater than B, this becomes 1 and the rest becomes 0. And if A is lesser than B, this becomes 1 and the rest becomes 0. Hope that's clear. That is what a comparator does basically. Okay. Is that clear? Let's see. Yeah, it's clear. Cool. I mean the action at the moment, no available. Huh. Okay, cool. All right. Now, now that what a comparator is like clear, we'll get into the next component, which is a multiplexer. Okay. No, a multiplexer is interesting in the sense that I'll tell you what it does. Okay. we're gonna talk about a 4-to-1 multiplexer. Okay, a 4-to-1 multiplexer, basically it takes in 4 data inputs. Okay, 4 data inputs and 2 signal inputs. 4 data inputs and 2 signal inputs, which gives us a total of 6 inputs for the IC itself, for the circuit itself, and it gives out one output Y. Okay. Now, what a multiplexer does basically is, let's say these are your 4 inputs, right? They can be whatever, they can be 0 or 1. Essentially, a multiplexer lets one of the 4 pass through to Y. Okay. Either D0, D1, D2, or D3, it lets it pass to Y. Okay, let's forget about enable for now. Okay, this is E. It's not really relevant. Anyway, D0, D1, D2, D3, it lets one of those pass based on what signal inputs you give. Okay, S1 and S0. Now, I'll tell you how it works. Okay, let's say my signal pins are S1 and S0. If my signal pins are 0, 0, okay, both S1 and S0 are 0, D0 gets through. Y becomes D0. If my signal pins are 0, 1, D1 gets through. Okay. If my signal pins are 1, 0, D2 gets through. D2 gets through. Okay. And if my inputs are 1, 1, D3 gets through. Hope that's clear. That is what a multiplexer does. That is what a 4-to-1 multiplexer does. It takes 4 inputs and gives out one output based on 2 signal inputs. Okay, is that clear? Now, in the real world IC, which is called the 74LS153, what do you have? Let's see. Okay, so the pins. Okay, so this IC, right? It has 2 4:1 multiplexers. Okay, it has 2 multiplexers. I'm gonna talk about only one of them. The other one also you can use like simultaneously with the same chip. Okay, so you have 2 multiplexers. It's named A and B here. Okay, so for multiplexer A, your 4 inputs are these: I0A, I1A, I2A, and I3A. And your output is just ZA, which is over here. Okay, and your signal pins. Now, here's where it gets interesting. Your signal pins for both of the multiplexers are common. Okay, so in this case, in your IC, both multiplexers are controlled by the same signal inputs S0 and S1. Okay. Similarly, your multiplexer B has 4 inputs, which are these, and one output, ZB. Okay. Forget about this for now. Again, this is the enable pin. Okay. So, and you for as for any IC, you have VCC and ground as well. Is that clear? Is there an 8-to-1 multiplexer as well? Yeah, there is. With 3 as inputs. Yeah, there is. Theoretically, there's like any number of input pins for a multiplexer, but yeah, an 8:1 multiplexer also exists. Don't ask me why I know this. The IC for that is 74LS157, I think. Oh no, that's different. Sorry. No, that is a 2-to-1 multiplexer. Forget what I said. But yeah, there is an IC for 8:1. Okay, cool. All right, let's move on. Oop, I did something, bro. Sorry. Yeah. Okay. Now this isn't really a digital circuit component. I just wanted to cover it to like make sure you understand what I'm gonna show next. But this is a 7-segment display. Okay. It has it's basically I'm sure you've seen it somewhere like in traffic signals and all that. Okay. it has 7 segments, and based on what inputs you give, it displays a certain like pattern or a number in this case. Okay, so you have 7 inputs which control each of the 7 LEDs or the 7 segments. You have A, B, C, D, E, F, and G, and you have a decimal point. I mean, like, it controls the little decimal point over here. Okay, and it's interesting because it works through a common cathode or a common anode system. Okay, so if you give, let's say, it's a common cathode, which means both of these COM pins are at 5 volts. You need to give it 5 volts. Then the entire circuit becomes like active low. So if you give, for example, B a 0 volt, right? If you give it a 0 volt, suddenly there's a difference between COM and B, right? COM and B. So there's a voltage difference between COM and B. Therefore, this lights up. Is that clear? Yeah. So that's how a 7-segment display works. You can use different signals you get from other components to make this light up however you want. Yeah. Is that clear? Looking for one response. After that, I'll move on. Cool. Okay. Right. Okay. Next up, I sent this image in the group. This is something I built myself for my lab. Okay. So this is like just okay. So I wanted to show this to you because I want you to realize that this is not like fully theoretical. Okay. This all of these concepts, they serve an actual purpose in the real world. So I'll tell you what this is. See, I have used some circuitry which I haven't covered yet. I will get to it later. I haven't covered yet, but essentially what it does is it counts up. It's like a traffic signal light. Okay, it counts up. So it goes from 00 to 01 to 02 all the way up to 15 because it's a 4-bit counter, and then it goes back to 0 again, and it does it again with a frequency of 1 second, 1 hertz. So it's like a second counter basically. Okay, and you know what the beautiful part is? If you realize from like whatever we've like covered from the start of the session, there is no hand waving at all, except for if you consider logic gates as your fundamental like unit of a circuit. Using just logic gates, you can build something which serves a real purpose in the world. Isn't that so cool? Like I find that like incredibly interesting. Yeah. Yeah. So this is what I built. This like it takes in as you can see, like there are blue wires over here. No, they're for something. I forgot what it is, but it's some input you give, and then it takes it, and then it counts up. I'm not really sure, but yeah, it takes logic gates as your fundamental like, unit, and it builds something useful in the real world, which is awesome. It's amazing. Okay. Cool. All right. Now we'll move on. Now these are called. We'll move on to something called memory elements. Okay. Memory elements are used to for are used to give the circuit memory basically. So if you want a circuit to remember previous inputs, okay, you use a memory element. Okay, so off the top of my head, I'll give you an example. Let's say I want, okay, let's say I want uh, okay, so I want a circuit. Okay, some circuit I have one input for that circuit. I only need one output for that circuit. Okay, if my input gets 3 consecutive ones, okay, 3 consecutive ones, only then should my function give me a 1? So like let's say I have a stream of bits coming my way, coming to the circuit, okay? Stream of bits which can be 1 or 0, okay? Let's say it encounters a 1. It shouldn't go it shouldn't give 1 as an output just yet. Okay? It needs to wait for other inputs. So after that your second input, let's say it's 1 also. Still it needs to wait. Only when your third consecutive input is 1, it needs to give you a 1. And if a 0 interrupts it, it needs to reset again. Is the problem statement clear? That is, I need to build a circuit which does this. And it's not really possible from just logic gates, because you're not giving it the ability to remember previous inputs. That is where memory elements come in. And I'm going to talk about flip-flops, which are memory elements. Okay. These are used to give the circuit memory. Okay, so there are three flip-flops. Three types of flip-flops that I'm going to talk about in this session. They're called the D flip-flop, JK flip-flop, and T flip-flop. Okay. D flip-flop is the simplest one to understand. So, see, now this element, this whatever this is, okay, it takes in two inputs at a time and it gives one output. Okay. And it is such that, okay, it's such that whatever I give as my D, as my input, that's what it reflects in Q. Is that clear? That's what it reflects in Q. So if this is my truth table for this, I want you to understand this clearly. There's Q, there's D. Okay, these are your input parameters. And there's Qt plus 1, which is your next iteration of Q. Okay, that's your next, what your Q will become. And what it'll become depends on Q as well as your input D. It depends on your current Q and as well as your D, your input. But in the case of D flip-flop, it doesn't really matter, okay? In the case of D flip-flop, your Q does not affect your next Q in any way. As you can see, whatever it is, whatever my D is, my Q just becomes whatever D I give. So if it's 0, it becomes 0. If it's 1, it becomes 1. If it's 0, it becomes 0 again. If it's 1, it becomes 1. It doesn't matter what the previous Q is at. Okay, it doesn't really matter. Okay, that is your D flip-flop. Now, what is the enable pin? This is what enables it. This is what enables it to have a sort of memory holding capacity. Okay, so how do you think your computer or whatever you're watching this on holds memory in itself? It holds it by storing some zeros or ones, like some collection of zeros or ones in a meaningful way. Okay. So an enable basically, okay, so if my enable is 0, it doesn't matter what my D is. My Q will hold. Okay. It doesn't matter what my D is. My Q will just hold the value it's at right now. Okay. If you're giving 0 to an enable, you're essentially asking it to do nothing. Just whatever value Q is at, you're just gonna ask it to hold it, no matter what. Only when enable is 1, okay, only when enable is 1 does D affect the value of Q. When enable is 1, it's like a gate. When enable is 1, the gate is open. The D can affect Q in whatever way it can. When enable is 0, it doesn't matter what D is. Q just holds that memory. That way, you have a sort of like way of holding data. It's not temporary anymore. It's real data which is stored somewhere. Okay, using flip-flops. Okay, I hope that's clear. Okay, now I hope whatever D flip-flop is, I hope that's clear. Okay, let's just check once. What do you guys think? Camera coming. Oh, my bad, guys. Sorry. Okay, I did not think of that. Uh, it seems that my camera is. I don't know what to do about that. I'll just keep it over here, maybe. I hope that's clear right now. Hope you guys can see. Uh, Sorry about that. Do you want me to explain it again? Like, I'll go over it quickly, okay? See, D, whatever D is, it becomes the next queue. It doesn't matter what the previous queue is. How exactly does the flip-flop hold the data when enable tells it to stop receiving inputs? Well, okay, so I get your question. Uh, it's more like designing. Okay, think of enable as another input. Okay, think of enable as another input of the little like element itself. If enable is 0, you're asking it to shut down all operations. You design your circuit in a way that enable acts as a sort of like halt in operations. Okay, so when your enable is 0, your queue just remains. You design your circuit like that. I can get into how what exactly is inside a memory element. Okay, but it's like kind of beyond the scope of this session actually. Like I can tell you it's fundamentally just made of like different gates, but they're arranged in a way such that the output, so like whatever gates are here, the output is fed back into the gates itself along with the input and like enable in such a way that it kind of holds memory. I hope that's clear. Like, if I get into how it's actually like working, it'll take like way too long. But yeah, when enable 0 is the input perceived by the flip flop. No, not at all. Like when enable 0, nothing happens. So does Q act like a container when enable is the lid? Oh yeah, yeah, sure. That is a decent intuition. Yeah. Okay, cool. Right. Fine. All right. D flip flop. Hope that's clear, guys. JK flip flop. If you understand what D flip flop is, JK flip flop basically, you have two inputs, JK and an enable pin. Okay, enable acts as the same way. Whatever JK is, it doesn't matter if enable is 0. Q is gonna hold on to the previous value. Okay, so let's get into the truth. Let's get into the truth table. Okay, if J is 0 and K is 0, okay, okay. So I want you to think of J as a sort as set. Okay, think of J as the set input and K as the reset input. Okay. If J is 0 and K is 0, okay, if J is 1 and K is 0, if J is 1 and K is 0, okay, it sets the flip flop. In that means setting the Q to be 1. Okay, if J is 1 and K is 0, Q becomes 1. It sets the Q. And if J is 0 and K is 1, it resets the Q. So it resets Q back to 0 no matter what the previous Q is. Got it? Okay. You can observe that in the truth table as well. J is 0, K is 0. If J is 0 and K is 1, it becomes 0 over here. If J is 0 and K is 1, Q becomes 0. And this configuration, it doesn't matter if in this case, it doesn't matter what the previous Q is, it just resets. Okay, now when when both J and K are 0, when both J and K are 0, okay, it does nothing. It just retains whatever Q is there. Okay. Okay. If J is 0 and K is 0, it doesn't do anything. If J is 1 and K is 1, it resets. It flips the Q. So whatever Q was, it just interchanges it. So it's like toggle. It toggles the Q value. So to summarize, one second. To summarize, okay. J K. If it's 0 0, it retains. If J is 0 and K is 1, it resets, which means it goes back to 0 no matter what the previous Q was. If J is 1 and K is 0, it sets it. And if both are 1, it toggles it. It complements it. Hope that's clear, guys. Okay, cool. Now, this is essentially what the truth table is trying to convey, based on previous Q and all. You can go through it; it'll make sense. Okay. Coming to the T flip flop. Okay, it has one input T, and it has an enable. Okay. Essentially, T can be thought of as the toggle input. So if T is 0, if okay, let's go back to the whiteboard. If T is 0, sorry, if T is 0, retain. If T is 1, toggle. Okay, that is what a T flip flop does. These are your three types of flip flops that I'll be discussing. There are more, but this should be enough for you to understand what I'm going to talk about next. Okay, is that clear? In the OR gate, we did 1 plus 1 is 1, but 1 plus 1 is 0. Ah, okay. This is a okay. Good question. Okay, like what Neil the Ganto Paul. Sorry if I butchered your pronunciation, but what he's asking is okay. I'll get back to other question. Just give me a second. Okay. Even though I'm talking about plus, I'm talking about like binary addition before. Even though I'm talking about the same symbol plus, in the case of representing functions, it means OR gate. So when I'm saying x plus y, it means an OR gate. Okay. It means this. But when I'm talking about binary addition, okay, when I'm talking about binary addition, it means addition simply. So those are two separate operations which happen to share the same input, same like symbol that we use. So hope that's clear. That plus is OR gate and other plus. Oh yeah, yeah. Okay, so Aditya just answered that question. Anyway, yeah. What exactly is retain, reset, set, and toggle? Okay, so retain is retain basically means it retains whatever the previous value of q was. Okay, it retains that value of q without changing it. Reset means whatever value of q was before, doesn't matter, it switches back to 0, the new value of q. Okay, set essentially means whatever value of q is there, doesn't matter, set it to 1. Okay, and for toggle, whatever the value of q was before, just complement it, just flip it. That is what toggle is. How that's clear? Yeah. Does the enable work in the same way in the other flip flops as well? Yeah, absolutely. When enable is 1, that is when the flip flop is functional. Else it holds that value of q no matter what input you give. Cool. Okay. All right. Let's see. Cool, guys. Okay. Hope it's clear. Hope all of this makes sense. Oh, one more thing. A little bit of a tidbit. Okay. How do you get this? Is just like this doesn't really like have any real world implications. But if I'm giving you a JK flip flop. Okay, I'm giving you a JK flip flop, and I want a T flip flop out of it. I want you to connect different stuff together so that I have a T line, and I want to give that T line somewhere in this somewhere into this flip flop so that it behaves like a T flip flop. Can anyone tell me how you can achieve that? And same enable in multiplexer. Yeah. Whatever enable that I hand waved before, it just means that so if enable is low, the IC just stops working. Okay. Does anyone know? Just think about it a little bit. How do you achieve a T flip flop, the functionality of a T flip flop from just a JK flip flop? Make K always 1. Not exactly. See, I want you to think about that because K equal to 1 means it either becomes reset or toggle, right? Same input to J and K. Yeah, exactly. So if I take whatever t is given, if I connect it to both J and K, if my t is zero, if my t is zero, it retains, and if my t is one, it toggles. Does that make sense? Yeah. Cool. Okay. Good job. Right. What else? Okay. Now that everything's clear, we'll move on. Okay. Oops, sorry. Why do we need memory elements in circuits anyway? Yeah, as I said, I talked about this before. When we need a circuit to remember previous inputs, like the example I gave before, when you have a stream of bits, and you need a circuit to detect three consecutive ones, and only when that case occurs, it gives a one output, else it gives a zero output. In cases like that, which tend to occur, which you tend to use more times than not, actually, you need a memory element in the circuit. Cool. Okay. Now, this is the problem statement that I was talking about before. This is what a circuit with which outputs one if three consecutive ones are given. Like the same problem statement, this is the realized circuit for that. It's pretty like badly drawn, and it's straight from my Sem 2 notes, bro. Like but like yeah, this is the circuit which does exactly that. Now, I want you to realize, okay, remember how I gave you like a very procedural way to realize any sort of combinational circuit before using SOP. Yeah, before whatever problem statement I gave you, you can just like step by step write the truth table down, write the terms, and like add them together, right? There is a similar way for you to design any sequential circuit. So like right now, if I ask you, okay, I want a circuit which gives me which outputs a one if three consecutive ones and a zero. So like I want a 1 1 1 0. Only when I receive a 1 1 1 0 will the function or the circuit give a 1. With there is a method for you to realize that as well, but like that is kind of beyond the scope of this session. I actually encourage you to like look into how to generate sequential circuits like that. Anyway, a sequential circuit, okay, I forgot to define it formally. A sequential circuit is nothing but a circuit which remembers past inputs. Okay, for you to design any sequential circuits, there is a set procedure. I'll give you resources for that. I'll give you my notes also if you want. But yeah, um, there is a set way. That is what I used to derive this circuit myself. Now, why I showed this example was to introduce you to something called the clock signal. Okay, clock signal. Okay, so okay. Anyway, a clock signal basically, okay, if you guys have played Minecraft before, okay, it's there's something called a tick speed, right? Similarly, okay, so a clock circuit is basically, it defines the minimum rate at which different memory elements can shift their value. Okay, I'll tell you how it works. A clock signal is just a varying signal in time. It's like a square signal. Okay, so let's say my clock frequency is 1 second. Okay, for 1 second, my clock signal will be zero. For the next second, it'll be one. It'll go to zero again, 1 0 1, and so on. Why is this important? It's important because recall the enable pin from before. If you connect the enable pin to such a clock signal, okay, you're essentially defining a frequency at which it's allowed to change. So when we'll look at this in more detail, okay, 0 1, cool. One second. Yeah. Okay. So when it's zero, okay, when it's zero, you're not allowing the memory element to change at all. But when it's one, you're allowing the memory element to change. Okay. And the input can change however it wants. So, like, see, for a D flip flop, the input is in your hands. So, in the course of it being one or turning one, which is 1 second, your D can flip as much as it wants, right? Okay, it can flip as much as it wants. It doesn't matter. What matters is at the very end, whatever your input is, whatever your input D is, at the very end, it takes that, and when it becomes zero, it locks it in for that next pulse. Is that clear? That's the best way I can explain it. I hope that's clear. That is how you define a that is how you work with data basically. So you lock a data, lock like a binary bit for one clock cycle. You do something with it, and then you move on to the next clock pulse. Hope that's clear. Let me know if it is. I can explain it again if you want. The clock signal is connected to enable. Yeah. Is it clear, guys? Do you want me to explain it again? Oh, okay. Hope it's clear for everyone. It's the best I can do. That was a pretty good explanation, I feel like. But yeah, anyway, when it's one, you let it shift however you want. It doesn't matter. At the very end, whatever your value of D is, it gets logged in for your next second. Okay. For your next second, it gets logged in. Okay, in your memory element. Okay. Is it clear? Cool. We'll move on. How to design a sequential, yeah, okay, so what this slide is saying is, again, as I explained before, there is a set pattern, there's a set algorithm that you can follow for any problem statement, uh, to design any sequential circuit you want. Okay, now these are additional concepts under digital systems that I'm not covering right now. Okay, these are counters. Essentially, this is a counter is a type of sequential circuit design, sequential circuit which counts up. So if it's a 4-bit counter, like I designed before, it goes from 0000 0001 0010 and so on. If you feed it a clock signal, so as you feed it a clock signal, it shifts every single cycle. I hope you get it. Like, a clock signal is an input you give to a counter so that it knows when to like count up. Okay. And there's also something called a finite state machine. Now, I'm not going to explain what it is because it'll take way too long to explain. But it's very interesting actually, a finite state machine. I'll give you resources if you're like actually interested. Do check it out. But essentially, a finite state machine defines a bunch of states that a circuit can be in. So let's say you have two flip flops, okay? Two D flip flops. If you have two D flip flops, you have four unique states that the circuit can be in. So it can be 0, 0, 0, 1, 1, 0, and 1, 1. These are your four states. These are your four states of Q, right? Right? Okay. So yeah, that is how a finite state machine is defined. You can also like design any finite state machine the same way you do for a sequential circuit. It's all very interesting stuff. I'll give you different resources later, but yeah, that's pretty much it. These are stuff I'm not going to cover in this session. Cool. Okay. How is tick rate and frame rate related? Tick rate and frame rate. Those are very different things, bro. Like frame rate, I guess they're the same thing under different contexts. Like a frame rate is defined for like video, where you can, it's like how many frames are in like the video, right? Per unit time. And tick rate is like the same thing, but like in a different context. Those are two different things, but share the same idea. Okay. Now we're getting to the fun bit, bro. Okay, registers. Okay, now a flip flop stores one bit of data, right? It stores one bit of data, either a zero or a one. Obviously, that's not enough for you to like actually do stuff. Like in your computer, a one bit is not going to do anything. Okay, what you need is a register. A register is a group of flip flops used to store a multi bit binary value. Okay, so I think it's pretty self-explanatory. Like the first diagram, you see four. Sorry, over here you see this is an n-bit register, which essentially means there are n D flip-flops. Okay, there are n D flip-flops, each storing one bit. Okay, so you're essentially allowing the circuit or this register, this element to store n bits of information at a time. Okay, there's nothing more to it. It's just a bunch of flip-flops. Okay, now a shift register, on the other hand, okay, a shift register is nothing but a register which is capable of shifting its stored bit data by one bit position. Okay, so what that means, that's a bunch of words. I'll tell you what it means. So let's say, sorry, uh, we'll, so let's say these are your flip flops. Cool. Let's say I'm connecting these like this, and I'm designing it so that if I want, let's say, at t is equal to 0, or like at some point, my data is 1011. So I have four registers. Sorry, I have four flip flops. They're connected like this, and they're stored. They have a 101 and a 1 stored. Now a shift register basically has the ability to shift like whatever data it's stored through to the next flip flop. So if I wanted to, I can give it a clock signal which shifts it to the next flip flop basically. So this bit 1, it moves to the next flip flop. The 0 moves to the next flip flop. This 1 moves to the next flip flop, and this 1 can be connected anywhere. Like it can loop back. It's up to you. It's up to how you design it, or you can use it to like convey any like information to some other part of the circuit, right? Cool. And it can be designed such that each flip-flop's bit can be read or can be accessed through this point, as you can see in the diagram, right? Hope that's clear. Speaking of clear, there is an input called clear, and this essentially just clears everything. So it clears each flip-flop, it resets it to 0. Cool. Okay. Camera. Oh my god, I did it again. I'm so sorry, guys. I'm so sorry. I'll move it back. Oh, sorry. Yeah. Is it clear? Yeah. Cool. Okay. All right. All right. Okay. Now we have completed the digital systems part of the session. Okay. Now the ultimate payoff to all of this, information that I've been like talking about, is a microcontroller. Okay. A microcontroller it uses every single concept that we've talked about so far and encompasses it into one chip which can do your job, which can do your job, uh, which can do any job you want. And this is where all of this mostly theoretical stuff meets robotics. Okay, it's pretty cool. So a microcontroller, it's another IC. It looks like another IC, but it's a single IC. Okay, it has multiple registers, memory, a processor, into all of it into one chip, which can be programmed. I'll tell you what that means. It can be programmed using code. Okay, it can be programmed to accept inputs, accept 5-volt inputs or 0 inputs, and process them and uh, output other voltages accordingly. Okay, so for example, this is a microcontroller. It's very widely used. It's called the Atmega 328P. Okay, it looks like this is how it looks like in real life. Okay, and this is the pinout diagram for the Atmega. Cool. Now uh what I've marked in green is just the power pins. Okay, I'm not gonna go into what each of these pins does. Okay, this is mostly as I'm gonna treat this as like more of a nudge for you towards exploring the world of microcontrollers rather than me explaining everything. Okay, because we simply don't have that kind of time. I'm just gonna give you a brief overview. Cool. So the um, pins that are marked in green are the power pins. So you have your classic VCC. You have two ground pins. Okay. You have A ref and A VCC, which are see, this kind of dips into analog territory. Okay, we've talked about digital signals. Digital signals meaning a signal can either be high or low, or 5-volt or 0-volt. An analog signal, it it can be any real like voltage. It can be 2.2 volt. It can be 4.7 volt, and these are used when there are like real world sensors, like a temperature sensor, for example. It can't really convey information in the form of like digital signals, right? So if it measures a certain temperature, it has to um it has to convey that temperature measurement in the form of a voltage, and that voltage is not going to be either 0 or 5. It's going to be something in between for it to convey what it measured, right? So ARF and AVCC have to do with working with analog inputs, which I'm not going to get into. Just know that these are power pins. Okay, you need these for it to work. Now every single other pin, okay, every single other pin are all of these pins are called GPIO pins, general purpose input output pins. So all of these have their own little like flip flop attached to them. Okay, I'll tell you what exactly is attached to each pin, but there is some sort of memory attached to each pin, and it is capable of dynamically changing between input and output. Okay, so it can take an input and then it can give out output based on how you program it to work. Okay, is that clear? You guys have any questions? It is 2 hours. I'm gonna wrap it up in like around 10 minutes. It's going on for longer than I expected. Um, but yeah, looks like a centipede. Yeah, cool. Any questions, guys? Uh, why? Wait. What is the use of two ground signals? Okay, well, um, see, for a more complex IC like the Atmega, right? you have to route like voltages in some way for it to work. And in more complex circuitry, like what's present in the Atmega, it's better if to minimize the amount of wires and the amount of circuitry you make for the same input by giving two inputs. So if there are two grounds, you give both grounds the same voltage, and both of them are used in different parts of the IC, and it reduces like noise, and it reduces any losses you get uh, from like routing it too much around the IC. Is it like a flip flop with will store 0 or 1, which will change how the pin works? Yeah, that's exactly right, actually. And we can change the flip flop with pin mode in the code. You're very close. You're very close. But pin mode is like it dips into Arduino. I'll see. The Atmega is the Arduino is an abstraction of the Atmega. Atmega, you program it using very bare metal C. Okay, you go into like the register level, you change registers and you do it. But pin mode in an Arduino, it makes it more user friendly for you to determine what each pin does. But yeah, that is a good analogy. Like you don't use the pin mode, you don't use pin mode exactly, but you use some command in C programming to alter a bit in the flip flop, in some flip flop, to alter how each pin behaves. Okay, cool. It's already like 2 hours. We're already 2 hours in. I'm gonna wrap it up like pretty quickly. Just like give me 5 more minutes, okay? Okay, cool. So now I'll tell you how an Atmega works, like very, very in a very surface level way. Okay. So as you can see, there are there are three ports in the Atmega. There's B, there's C, and there's D. And what a port is a port is just a collection of 8 GPI opens. Okay, it's a collection of 8 GPI opens. So over here, you have 8 pins for the B port. You have B, B1, B2, B3, B4, B5, B6, B7, and okay. So one of them has 7, but okay. So B has 7 pins, and C and D have 8. Okay, so B has 0 to 7, and C has 0 to 8, 0 to 7. B has 0 to 1 to 7. B has 1 to 7. Okay, now B, C, and D are called ports in an Atmega, and each port has three registers, three 8-bit registers associated with them. Okay, three 8-bit registers. Think of 8 flip flops in a row, which you can store data into. Okay, now uh each with okay, so each port has three 8-bit registers. So those three 8-bit registers are called DDRX, pin X, and port X. Okay, DDRX, pin X, and port X. Cool. Now for port B, X becomes B, so it's just like naming. So for port B, it's DDRB, pin B, and port B. DDRA, pin A, and port A. You get the idea. Cool. Now an 8-bit register has 8 bits. No, it has 8 bits. For the DDRX register, there are 8 bits. Each bit, whether it's a 0 or a 1, determines the use of each pin in the port. So each of these flip flops, let's say the first flip flop is for PB1. The first flip flop is designated for PB1. If it has a 0, it acts as it acts as an input pin, and if it has a 1, it acts as an output pin. Okay, so a DDRX register determines how the pin is used for each port. Cool. Now, in the case that a pin is designated to be input, okay, It stores. Okay, so what the pin X register does is it takes the voltage reading which is given to each pin and it stores it in the flip flop. So, for example, uh, let's talk about pin B. Okay, pin B register, under which I'm talking about the B2 port, PB2. This has one flip flop associated with it. Okay, and what if it's configured to be input? Whatever it's whatever voltage it's subjected to, it stores it. So if I give it a 5 volt, it stores a 1 for it, for the processor to work with, however I program it. Okay. And port, similarly, if it's configured to be output, uh, it stores whatever value is to be outputted from the pin. Okay, I hope that's clear. Is this clear, guys? Is it buffering? Oh no, not again. Is it buffering? Understood. Cool. Okay. All right. All right. All right. Okay. So no buffer. Cool. Cool. Okay. Now let's move on. Okay. Now that you understand how registers actually uh, affect the working of the IC. Oh, one more thing, by the way. Apart from these registers for each port, there are multiple other registers inside the chip itself, which determine. Okay, so a GPI opened, right? For example, PC5. Whatever's given in the in brackets, this pin also serves this purpose. I won't get into what this is. It's mostly for communication. Okay, but this pin also serves this purpose, which is SCL, which is used for communication. Okay, with different ICs if you want. How you assign this pin to carry out that function in brackets is by assigning uh, some flip flop inside the atmega uh, to a 0 or a 1. You determine the use of each pin by essentially flipping flip flops. Is that clear? Each pin has different use cases apart from being a GPI open. And to access those, you need to alter different registers inside the atmega, which you can do by programming it. Okay, cool. Now, let's move on. I'll give you a very simple code. Okay, very simple atmega code. Okay, I won't go into what this means. But essentially, how you program an atmega is by altering different registers to mm, to like make it work according to what you need. So here, very surface level understanding of the code is I assign DDR1 to be 1. What does that mean? I assign PB5 to be 1. Basically, PB5 determines the um, PB5 determines what the what the pin PB5 is used for. And since I'm assigning it to 1, it is assigned to be used as an output pin. Okay. Now I'm defining a while loop under which port B. Okay, port B is the output pin. So I'm changing it to a 1. Basically, I'm outputting a 5 volt through that pin, through the pin PB5, and I'm waiting half a second, 500 milliseconds, and I'm changing it to a low. This means low, by the way. Okay. So if I'm changing it to a 1, I'm waiting half a second, I'm changing it to a 0, I'm waiting half a second, and it keeps cycling. Cool. Now what this means is that if I hook up an LED, to the port PB5, it's gonna blink every half a second. Is that clear? This is how you use very bare metal C to program an atmega. Infinite loop, yeah. It's not a bad thing. Oh no, it's that's how you program. That's how you program like and blinking LED to blink forever. Cool. Now we'll get to the Arduino Uno. Okay. Does this look familiar? This is an Atmega. I hope you guys know what an Arduino is. So if you don't, it's basically a very simple to use board which you can build stuff with. Okay, and it works on an Atmega 328P. This is the Atmega, and it's designed in such a way to make your experience so much more like human friendly. See, this code has so much like gibberish to people who don't know what's going on. Registers, they don't know what's going on, right? They don't know what a register is. They don't know what bits are, right? If you want an LED to flip from being on and off every half a second, there is a better way to do to achieve that than going into the register level, and that is what the Arduino Uno does basically. Okay, I'll give you the same code in I'll give you the same code which achieves the same purpose while using an Arduino instead of just the Atmega. See how much more user friendly and simple it is. Okay, so a pin mode. This is what I was talking about before. A pin mode basically assigns a pin to an output pin, and then a digital write it assigns it a 5 volt output signal, which turns the LED on, waits 5 seconds. Waits half a second, and turns it to a low, and waits half a second. Okay, and void loop basically means it goes on forever, and void setup means it goes on once. So it's set to output and it keeps flipping on and off. Yeah, cool. All right, so that is pretty much it for what I wanted to cover this session. Additional concepts to explore after this session, I've listed a bunch of them over here. I did cover these on a surface level. I talked about K maps and how they simplify binary circuits. I talked about sequential circuit design, how there's a set algorithm to design any circuit for any sequential circuit you want, a problem statement you want. I talked about counters, finite state machines, and if you want to actually build stuff, build like pretty complex stuff using the Atmega and the Arduino, you can look up tutorials. If you want, I can send reference links and like resources for you to learn all of these. But yeah, these are stuff I would encourage you to look into after the session. Okay. Again, this is the attendance Google form link. We've reached the end of the session. Just scan this if you haven't already. Fill out the form. You'll get attendance. Video is covering bottom left part again. Oh, sorry. Oh my god, bro. I keep doing it. Fine, fine. I'll just let you look one more time. 1 second. Yeah, should work now. Yeah. So these are additional concepts. Just look into these. Ask me for any links. I'll send them happily. Okay. This is the attendance QR code if you want to scan anything. If you want to get attendance. Thank you guys. That actually means a lot that you guys enjoyed the session. How did you achieve this amount of fluency and confidence in just 1 year? Well, it's more in college, right? If you're if you have like an electrical core to some extent in your coursework, most of this I covered in my coursework only. And about the Atmega and the Arduino, that's stuff I learned on my own, which you can do as well without any um, coursework in like college itself. You can do it on your own. But yeah, it's just a combination of coursework and personal interest. You should make YouTube channel to teach robotics or physics. You'll make a great teacher. Thank you. Hmm. Siddhant Dadich. I wonder where I heard that name before. Okay, cool. All right, guys. I'm so glad you enjoyed the session. Are you very interested in robotics and all? Yeah, actually. Um, I'm less interested in robotics and more towards like electronics, actually. As I've realized, I thought I was interested in robotics before. I'm still exploring what I'm fully interested in, but it's more. I know it has to do something with electrical. All right, guys. That is it for the session. The attendance Google form link is over here if you want to scan it. Thank you, guys. Thank you, guys. I hope you. I'm so glad you enjoyed the session. All right, cool. I'll see you guys later. Uh, if you have any questions or anything to like talk about, just like I'm in the group. I'm an admin. You can look for me. My name is Atit again. You can search for my number. If you want any resources, I'll just send them your way. All right, cool, guys. Thank you so much. I'll see you all later. Bye. Oops, sorry.